Pre-calculus Unit 1, Lesson 2, Functions and their Properties. Okay, we know that a function rule is a rule that assigns every element in the domain to a unique element in the range. Function notation, we have y equals f of x. Y is called the dependent variable, x is called the independent variable. Again, d is the domain, is the possible input values of the function, and the range r is the output values of the function. You can look at a vertical line test in order to be a function. So if you look at a vertical line, it can only intersect the graph in a single point. In the mapping diagram, you can only have one arrow that leaves each x. So if you have two arrows that leave an x, that can't be a function. If you have two going into a value, that is a function or could be a function. So for each one of these, is it a function? And to determine the domain and range, this would not be a function, because if we look at this vertical line, it intersects in 2 points, which is more than one. The domain is supposed to be, I'm not sure it's touching exactly, but it's supposed to be at -1 and go to 7. And then the range is supposed to be there from 2 to 7. Again, it's not perfect on the graph. For this one, it is a function because when we look at any vertical line, it never touches this curve in more than 1 point. The domain, of course, this goes all the way out to -infinity and to +infinity, but the ranges starts down at -infinity, but the highest it reaches is 4, and that 4 is included, so that would be -infinity to 4. For this particular graph, this relation is a function. Again, no vertical line ever touches more than 1 point. It goes out to -infinity and goes this way to +infinity, so the domain is -infinity to infinity. The ranges also go down to -infinity and up to +infinity, and of course, so that is, I said that it's a function. The domains of functions can be found algebraically using properties of the function or by a sign chart that includes any values with possible restrictions as values on the number line, and then we're going to give our solutions in interval notation. So for each function, find the domain algebraically and graph to find the range. And the things that we have to worry about are underneath a square root sign, we need things to be bigger than or equal to 0, or if they're in the denominator, they have to be strictly bigger than 0. We can't divide by 0, so any denominator can't be 0. And there will be other ones that we will look at, but those are the main two for now. So we have two things that we need here. We need 4 minus x to be bigger than or equal to 0 because it's underneath the square root sign, and we have x plus 1 that can't be 0. So we have two different conditions that we have to meet. If we solve that means x is less than 4. If we solve this, x cannot be -1, so -1 is in the region of less than 4. We have to take that -1 out, so the domain will be everything up until -1, and then we'll skip -1 and go from -1 to 4. So we leave out the -1, and then we start at -1, but we still leave it out, and we go up to 4, but the 4 is included. And then if you graph this function, you'll see that the range goes from -infinity to infinity. For this, when we have any sort of polynomial underneath, we're going to have to use a sign chart. So again, we need that to be bigger than or equal to 0. We're going to factor it. We're going to put each of the zeros on the number line. So we have zeros of 0, 4, and -4. Again, they have to be in the right order on the number line. And then we're going to pick values in each one and talk about whether the sign of those is positive or negative. So if I had -5, this would be positive, this would be negative, this would be negative. A positive and negative when multiplied together give you a positive. In here, -2, this would be positive, this would be negative, this would be positive. So we have positive, negative, positive. Again, multiplied together would give you a negative number. If you take in here like 2, this would be positive, this would be negative, this would be positive. Again, like that, that would be a negative overall sign. And if we take a number bigger than 4, this would be positive, this would be positive, this would be positive, for an overall sign of positive. Now we want bigger than or equal to 0, so we want the places where it would equal 0 and the places where it would be bigger. It's equal 0 at each of those 3 points, and it's bigger wherever it's positive, so that would be this way and this way. So we're going to go from -infinity and include -4. Then we have to include the single point of 0, and then we have to go from 4 to infinity with the 4 included. If you graph this, you'll see that the range goes all the way down to 0 and then goes up to infinity. At 0, of course, if we put 0 in there, we get 0. That is the smallest value that you can get. You won't see this single point on your graphing calculator, but it's actually part of the function. As the last example, we have a rational function again, y equals x plus 5 over x minus 2. The only thing we have to worry about is that we can't divide by 0, so x minus 2 can't be 0, so x cannot be 2. It's really the whole real number line except for that 2. We need to leave it out, and if you graph it, you'll see that the range, there is a horizontal asymptote of y equals 1, and therefore you have to leave that y out, and you'll have everything except the 1 in there. Now, other properties that we've looked at before are discontinuity points. So what are discontinuity points? A removable one would be if we're going along and there is a hole at that point and then it continues. Now, the function could be defined somewhere else, but as long as it's just a hole that you're jumping over, that's a removable discontinuity. A jump discontinuity means you're going along and then you might be here and then all of a sudden you jump up here to continue on that function. That's a jump discontinuity. And then infinite discontinuities are when you have a vertical asymptote. So you have an asymptote and maybe you're going up here this way, and you could start down here and go here, or you could go here, as long as that's going to minus infinity or plus infinity on the left and the right of that value. We also know about increasing and decreasing functions. So increasing, as the x gets bigger, the y gets bigger. For decreasing, as the x gets bigger, the y gets smaller. Constant or when it stays the same, so they show up as flat areas on the graph. Bounded below means it never gets below a certain value. Bounded above means it never gets above that. A function is called bounded if it has both a lower bound and an upper bound. We know about extrema, so there are local or relative minimum and maximum. And then there's absolute minima and maxima. A local one is the biggest or the smallest in an open interval around it. It doesn't have to be everywhere. Absolute has to be the absolute biggest or smallest thing in there. We know about symmetry. There's symmetry around the y-axis. That's where the part on the right side matches the part on the left side if we fold over the y-axis. And in that case, the function is an even function where the values for x and the opposite are the same values. So at 3 and minus 3, they're at the same height. At 4 and minus 4, it's at the same height, and so on. A function is symmetric with respect to the x-axis would mean that the part above the x-axis is the same as the part below that. In this case, y is not a function because you would have the same x with two different y's, so we won't see this type of symmetry with a function. A circle is symmetric with respect to the x-axis. And for another function, we have symmetry with respect to the origin, in which the function looks the same right side up as upside down. And in this case, the value at, say, 3 will be the opposite as the value at minus 3. So if I had 2 at 3, I'm going to have minus 2 at minus 3. They're going to be the opposite. Asymptotes, we know a horizontal asymptote is a horizontal line that the function will get closer to as x goes to plus or minus infinity. A vertical asymptote occurs at a point x equals a, meaning as you get closer to that, the y value is either going to go either up to plus or minus infinity. Vertical asymptotes arise by trying to divide by 0, and then end behavior is how the graph behaves as x goes out to plus or minus infinity. As some examples, this one is continuous in this function, so we go to here, except here it jumps. And then it's continuous again, only here there's a jump, and then it's continuous again. So the only points where it's not continuous are at minus 2 and 2. So we would say it's continuous on minus infinity to minus 2, and then minus 2 to 2, and then 2 to infinity. There are jump discontinuities at minus 2 and 2. It is increasing on minus 2 to 2. It's not decreasing anywhere. It is constant here, and it's constant here. It's bounded above by 5 because the function never goes above 5. It's bounded below by minus 5 because there are no function values below minus 5. The absolute maximum is 5, meaning the function never goes past that. The absolute minimum is minus 5, and that maximum occurs on the whole interval here and on the whole interval here. It's not at a single point, it's on that entire interval. This is an odd function because if I take the right half and turn it upside down, it will match the left half. Also, we can see that whatever we have at, say, 3, I'm at 5, and then at minus 3, I'm at the opposite, I'm at minus 5. The end behavior is as x goes out to minus infinity, it stays at minus 5, and as it goes out to positive infinity, it stays at 5. For this function, it is continuous except here there's a hole, and then it's continuous everywhere else. So the only point of discontinuity is minus 4, so we would take that out. That is a removable whole discontinuity. So even though the function is defined here, we could cancel that function value and put it down here instead, and then that would be a continuous function. We are increasing until here, then we're decreasing, then we're increasing, then we're decreasing. So it's increasing up until minus 2, and then it's increasing from 2 to 7. It's decreasing from minus 2 to 2, and then it's decreasing again from 7 and above. The absolute highest thing is 8, so that's an absolute maximum. There is no absolute minimum because this function goes down to minus infinity. There is a local minimum, meaning in this small region there is a local minimum of 3, which occurs at 2. There is also a local maximum of 5, which occurs at minus 2. The end behavior, as I go out to minus infinity, the y goes down to minus infinity. As I go out to positive infinity, the y goes down to minus infinity. This function has vertical asymptotes, so those are points of discontinuity. It's discontinuous at minus 4 and 4. So therefore it's continuous everywhere else though, because the other 3 parts are all connected. It's continuous on each one of those. And there are infinite discontinuities, as I said, vertical asymptotes at minus 4 and 4. In this section it's decreasing, and here it's decreasing. Here it's increasing, and here it's increasing. So it's increasing from 0 to 4, and then from 4 to infinity, and therefore it's decreasing from minus infinity to minus 4, and then from minus 4 to 0. It's unbounded because it goes way down to minus infinity and way up to plus infinity. It's an even function because the right half and the left half are the same. So if we were to fold this over the y-axis, this half and this half match, and this half and this half match. As I said, there are vertical asymptotes of x equals minus 4 and x equals 4, and then it also is getting close to the x-axis, so there's a horizontal asymptote of y equals 0. The end behavior is as x goes out to minus infinity, y goes to 0, and as x goes out to positive infinity, y goes to 0. For the fourth example, I won't go through everything, but there are jump discontinuities here, one at minus 3 and one at 1. This flat area would be both a local minimum and a local maximum. This has a horizontal asymptote of y equals 0 on the left. It doesn't have any on the right. And now there's another way of writing what we've been talking about as end behavior and getting close to things, and that's in terms of limit notation. So when capital L is a finite number, we say that as x gets closer to one number, the function number is getting closer to that limit. So again, this is the limit. As x gets closer to the number c, then f of x is approaching that number L. We can also go from either the left or the right, and those can have two different limits. So the left, meaning if you come from the left side, that's written as c from the minus, and then if you come from the right, that is c from the plus. The limit really only exists if that number capital L is finite, but even if it goes off to infinity, we can write this statement with either plus or minus infinity, but we have to understand that that really means there's really no limit. It's simply getting increasingly smaller or increasingly larger. So now if we want to write those in terms of this behavior, if we look, the ones where it got closer to, as x went out to minus infinity, this stayed at minus 5, and as this went out to positive infinity, that stayed at 5. So we would say the limit as x goes to minus infinity of the function is minus 5, and the limit as x goes to plus infinity of f of x is 5. For this one, As x went out to minus infinity, it went to 0. As x went out to plus infinity, it went to 0. And then when there are vertical asymptotes, there were also limits. As we go from minus 4 from the left side, of course, it decreases without bound, so it goes to minus infinity. As we go to 4 from the left side, it goes up to positive infinity. As we go to 4 from the left side, which is this one, it goes up to plus infinity. And as we go to 4 from the right side, it goes down to minus infinity. And then for this last one, as we go to minus infinity for the x's, the y goes closer to 0. And as we go to x from infinity, the y is going off to infinity as well. So that's how we would write those in limit notation. Again, all of the ones that are actual limits are the ones with finite numbers, and then the ones with plus or minus infinity, that just means that as it goes to minus 4, say, from the left, it is decreasing without bound, and this one would mean it was increasing without any bound. So we can also decide if a function is even, odd, or neither algebraically. We don't have to have a graph to decide that. We're going to simply put in minus x in the function, simplify by deciding if that minus x makes the term different than if it had x. Compare that with f of x. If it matches that, it will be even. If not, is it the same as minus f of x? If it matches that, it's odd. And if it doesn't match either one of those, then it's neither even nor odd. So if I want to look at this function, I have to find f of minus x. Well, again, f of minus x means wherever you see x, you put minus x. So instead of this x, you put minus x. Instead of this x, you put minus x. Remembering, of course, that if you want to put that in the power, you have to put parentheses so that you square the whole thing. Minus x to the fourth is just x to the fourth. Minus x squared is just x to the squared. And when we compare this, we see that these are the same. So f of minus x is equal to f of x. And that's the definition of being even, which means it's symmetric about the y-axis. If we put minus x in this one, again, we're now going to cube this, and we're going to put it in here. 2 of minus x cubed, well, 3 minuses make a negative, and then this minus times this minus makes a plus. If we compare these are not the same, so f of x is not even. Now if we look at minus f of x, meaning we change the sign of each of these, that is the same as f of minus x. That means that's an odd function, and it's symmetric about the origin. If we were to check both, that it's not equal to f of x and it's not equal to this, then it would be neither even nor odd. Remember that we can also find local extrema using our graphing calculator. For those of you with a TI, remember that you go to the calc menu, and in order to find the minimum or the maximum, like if I want to find this, I have to move to the left of where the maximum is and hit enter. Then I have to move my cursor to the right of where the maximum is and hit enter, and then enter again for it to guess and find this value of minus 8.47. For this one, if I want to move to the left of that, that would be on this side, so I would have to move my cursor on this side. And then if I want to be to the right of that minimum, I have to move to this side, and then I hit enter, and then I would hit enter again.